Hello, today I would like to present this paper titled Mammography Breast Cancer Classification Using Vision Transformers at the International Conference on Intelligent Systems Design and Applications. So the authors of this paper are Mohammed Eid Abi Mulud and Dr. Khalid bin Said, Dr. Mohammed Al-Ish, Dr. Usama Ayadi and Professor Munji Khairallah. This paper will be presented by me. My name is Mohammed Eid Abi Mulud, PhD student in National Engineering School of Sfax, Advanced Technologies for Environment and Smart Cities in Sfax University, Tunisia. All in this presentation, we introduce breast cancer disease, and secondly, state of the art. We propose some previous works in this subject research, and third, we explain the vision transformer system for breast cancer classification. After that, we present the mammography data set was being used in our work with the results obtained. And finally, we can conclude with some perspectives. Now, let's start by understanding what breast cancer is. So, the breast is a complex structure composed of 15 to 20 lobes, each housing tiny structure called lobules. These lobules consist of different forms of fatty, fibrous, and glandular tissue. Breast cancer can be developed in any area of the breast, and screening the importance of proper screening with the right imaging tools is crucial for women to be vigilant and proactive in their health. Now let's delve into the virus types of the breast. There are two main categories, benign and malignant tumors. For benign breast tumors, there is four subtypes. There is adenosis, fibroadenoma, pyridoxoma, and tubular adenoma. For these types, it's not dangerous. On the malignant side, there is also carcinoma, lobular carcinoma, myconos carcinoma, and papillary carcinoma. For these types, it's dangerous. Of the R. Based on the table, we see the majority of works use the convolution neural networks, and there are some new works proposed for other systems based on vision transformer architecture. In our work, we propose a self-attention transformer where it's pre-trained using different optimizers to present a high accuracy in breast cancer classification and with minimizing computational resource requirements and for reducing the prediction time. Now let's explain the vision transformer technique. So the vision transformer technique for image classification adopts the self-attention mechanism from the original transformer model used in natural language processing NLP. The process outlined in figure first we resizing the original image to 2024 by 2024 pixels, combining with the pre-trained vision transformer requirements. These resized images are subsequently divided into smaller patches, each measuring 14 by 14 pixels, resulting into 156 patches for each image. Before feeding the patches into the transformer encoder, several operations like flooding, sequence embedding, reliable embedding, and patch embedding are performed to prepare them for the classification. This integrated process culminates in the creation of a sequence of embedded patches uh, constituting the output of the transformer encoder. This output is intricately linked to a learnable class embedding. A crucial element for subsequent classification task, the output from the transformer encoder are then directed to the MLP head, a pivotal component in the classification process. The MLP generates a probability distribution of the labels corresponding to individual patches. Finally, this comprehensive approach ensures effective breast cancer classification, leveraging the power of vision transformer. And now the database used in our work, the DSM database, digital database for screening mammography. The dataset is readily accessible to the public and comprises a total of 30,128 images. For benign disease, there is 5,970 images, and for malignant images, there is 7,158 images. So, for our model parameters, we used for the image to 224 by 224 pixels, for patch size 14 by 14 pixel. We get for patches for each image 256 pixel, and we used 8 layers with 4 heads, and then we used 3 different optimizers, Adam and Adama X and SGD. Experiments and results. In this table we present all results obtained with 3 different optimizers, Adama X, SHD, with different evaluation metrics calculated: accuracy, precision, sensitivity, specificity, and advanced score IC, and also training time and average training time per epoch. So we see the best accuracy in Adam optimizer, and the best training time for Adama X optimizer. Now we see the confusion matrix for each optimizer, Adama X, SGD. And now the rock curve also for each optimizer. And in this table we compared our results with previous work. So we see VIT with Adama X get a best result with 633 seconds for training time. Finally, self-attention transformer model streamlines breast cancer diagnosis, minimizing resource usage and training time. So our future research focuses on parameter optimization, integration, diverse data, validation with real patients time, and exploring with large datasets to both diagnostics efficiency. Thank you for your attention.